Physics time. Let's pick a color. How about this one? Linear motion. Linear. This is a good color. This is a good marker. Motion. Define it at this time. Right now. What is it? Linear motion. And you can't use the word motion to start it out. It's not just her. It's not just her, Alexa. You should be defining this too. I'm going to give you a little sentence frame. It's going to be a noun in a adjective noun is what I'm looking for. Can't use motion, though. Okay. That'll work. Movement in a... What does the adjective linear refer to? Specifically, what kind of line? Straight line. Whew. It's like pulling teeth to get these kids to learn something. Movement in a straight line, as opposed to what? Okay, but that'd be more specific. What is a not straight line? What would we call that in math? A curve. We wouldn't say curvy. What's wrong with you? A straight line is linear motion, as opposed to movement in a curved line, which we would call circular motion. Even if the line doesn't make a whole circle, we still call that circular motion. But this is movement in a straight line. What kind of straight lines is there?
Sideways line.
Okay, we can start with that one. Horizontal, vertical line,
diagonal line.
others. Any other direction. We're going to focus, it doesn't really matter because one is the other. What's the difference between these two on planet Earth's surface? Yes, but on planet Earth's surface, why do we have such a thing as down on Earth's surface? Because of what force? Gravity. Gravity provides constant downward force. And we're going to talk about force, obviously, later in the year. But gravity provides constant downward force. Am I falling? In the physical sense. Maybe I'm falling emotionally as a teacher, like I'm getting worse and worse. But am I falling in the physical sense? No. Am I falling in love? No. But that doesn't matter because that's not what we're talking about. But am I physically falling? Physically here means relating to what, by the way? Physically means relating to, guess what? The class we're in. Physics. So am I falling in the physical sense? No. I am not falling. Why? Doesn't this say gravity provides constant downward force? Yeah, there's also floor force. This is me, except I forgot to make myself fat enough. There we go. There is a constant downward force on my center of mass called gravity, F sub g. But also, as I'm just standing here, this is me just standing here. You know how with my legs all spread out. Yeah. Of my haircut. There's also upward force, which is not constant, but it exists at this time. There's an upward force equal called the normal force. The floor is pushing up on me with an equal force called the normal force. Does that mean that gravity isn't existing right now on me? No, it just means it's balanced. So, am I moving in a straight line? Am I moving in a straight line? Okay, but look more closely. Am I moving in a straight line? I'm not moving at all because there's not a force acting on me. If the floor vanishes, if this paunch gets big enough that I then fall through the floor and the floor can't provide that normal force and I do fall, am I moving? Yeah, and specifically how? In a straight line. Yeah, down would be more specific, but in a straight line. So one type of linear motion is this, what we call free fall, where the only force acting on you is gravity. What does that imply? There's no air resistance. So free fall is used kind of loosely at this point in the understanding of mechanics, but it is called free fall. Your bell work was define the quantities involved in linear motion mathematically. Let's define them now. Give me one, Alexa. The quantities, mathematically. I want you to find them first in words, and I also want you to find them mathematically, but not until later. So, speed, and what's the definition of speed? I want to hear your definition, by the way. I don't know what you're reading, but I want to hear yours. Okay. Fastness. Sure. Whether how fast it is or not, right? Okay, what's another quantity we should define, Lily?
Acceleration.
Let's not do that one next.
Okay, let's not. How about velocity?
Okay, I want your definition of velocity, Lily.
Okay, it's speed, but it has a direction.
Speed in a given direction. Good. Another quantity that we should define. Alessica? I don't care about that one. Average speed is just mean speed. And I don't care about that one either. That's just speed measured at a certain instant. Although that one is interesting, as we found in the mechanical universe, that because we do have to determine that one through differential calculus, because there's no such thing as instantaneous speed in algebra. We can't divide anything by zero by an instant. Anyway, but besides that, we don't really want to. I talked all that I want to about that now. What's the other one we want to define? Lily almost did it, is a good hint, because she had said it, and I said, let's not do that one yet. Acceleration, yeah. Now define acceleration.
Okay.
Please define it. Okay, and so, yeah, and since it's all three of those things, since it's gaining speed or losing speed or changing direction, we could just call it, change in velocity. Let's define these mathematically. Speed, S equals, I'm waiting for you. You should know these equations. D over T. Distance traveled over time elapsed. Where? So let's write, this is how we always do the equations in here. S equals D over T, where S is speed, measured in what in the SI? What's the SI? Well, speed doesn't have a base unit, but using only SI base units, what is speed measured in? Meters per second, thank you. Lowercase d is distance, measured in meters, and t, lowercase t is time, measured in seconds. Sometimes you will see, I'm going to write this another way. I'm going to erase my disgusting body. I'm going to write this another way. V equals S over T. This is a more, I don't know, college-based, and this is the way they defined it on your mechanical universe, where V, without a line above it, is speed. S is distance traveled, or really displacement is what S is. And T is time elapsed. You can write it that way too, where S is displacement in this case. The reason I don't prefer that is because this was what, I don't know, D does stand for distance, and that's usually what we're using instead of displacement. Okay, so then velocity, V with an arrow over it. The arrow is very important. What does the arrow represent? Do you remember this from physical science? It's a vector, meaning that we have to define the direction that it is traveling. So V, in this case, equals what? V with an arrow over it, velocity equals, yeah, it's distance over time still, except we have to specify a direction. So we're just going to put here speed in a direction, as we already did, but just make sure you have a direction with it. Direction can be something like right or left. That's a relative direction. Up or down, that's a relative direction. But it can also be angles of west of north, for instance. We could have to say it's moving at 40 meters per second, 19 degrees west of north. And we'll talk about that when we get more into vector quantities. Very important. We could also call it, we can also say below the horizon or above the horizon for elevation change. But all of those become very important, and we talk about those when we talk about vector addition, which will be in the next chapter, I believe. Acceleration, mathematically defined as A. Should it have an arrow or not?
Yes.
Yes, it definitely should. It's a vector quantity. Equals, do you remember?
It's change.
Okay, which is what Greek letter? Capital, okay, capital delta.
Changing.
Look at this, right here.
Okay, so changing velocity.
Okay.
Over
I usually just put time, but change in time is also fine. And this is where A with a line over it is acceleration. What units do you remember? Meters per second or meters per second squared. Yep. Delta is change in any quantity. Did you notice that any of the freshmen had a delta H over the summer? What would that be? Yeah, it is change in height. I don't actually care about whether you noticed that, but that's what delta H would be, change in height. Delta T would be change in time. If you had 15 tacos at Taco Tuesday, you had a delta M, change in mass. So yeah, any quantity preceded by delta is change in. And then lowercase t again is time measured in seconds. So now we have, you can see that, velocity. You can see that we have meters per second divided by seconds, meters per second divided by second, which will give us meters per second, or meters per second squared. Any of those expressions is fine. Now where I want to, this is all review. This should all be review. Where I want to spend some time, let me just verbally, and you can write this down if you need to, but verbally, what are the 3 ways that acceleration can change? Yeah, okay, so increase in velocity, right? So decrease in velocity, change in direction. You should probably write those down if you don't already remember them. Obviously, some of us remember them from physical science, but if you don't, what are the 2 ways in which there is no acceleration? You remember? What are the 2 states an object can be in where it is not accelerating? At rest, so just staying still, and constant speed in a constant direction, right? Don't forget that one. People often forget that one, especially when we start talking about inertia, but don't forget that. Okay, so what we want to talk about now is free fall. There are 2 equations that we're going to use for free fall. You have all these equations written down, right? I should have said, does anyone not have these equations written down? Because then I would have been able to tell if everyone did. But oh well, it's too late. If you don't have them, you can get them from one of your friends, or you can please watch the video to review. Free fall. Here's someone's meaty hand. It's not that meaty. And here's an object. This is good.
Oh, look at that. Yeah.
I'm good at it.
Baseball? Softball. Oh, they got some colors.
It's Alexa.
It's Alexa. This is Alexa's hand. It's a softball, we'll say. It's a softball. It's being held poised above the surface, and it will be let go. Uh-oh, let go. What must happen as it falls? Let's talk about it from the perspective of forces, since you should remember that from physical science. First of all, right now, before it falls, what are the forces acting on it? Is gravity acting on it at all? Yeah, of course it is. It still has a weight. Gravity is acting on it. But what is preventing it from free falling? Probably the friction between your fingers and the palm preventing the ball from falling. Probably friction. You can imagine, the way we can think about is it friction, is if you had a heavier object which was providing more weight, a bowling ball for instance, you were palming the bowling ball, but you also had your hands really lubed up, like you had olive oil all over your hands and you were trying to palm the bowling ball, you wouldn't be able to hold it up. So it's probably friction holding it up. Anyway, as it just sits there, gravity is acting up. But then when we remove the friction, when we let go, now it's only under the influence of gravity. This is all happening in a vacuum, by the way. Alexa's on the moon. Alexa and her acrylics and her softball are on the moon. There is no air resistance, because air resistance just muddies this kind of thing. You should recognize that air resistance does exist and that it does impact this. But for the sake of the math, we're going to just have it be in free fall. The ball is falling. What happens as it falls? It gains speed. Yes, it gains velocity. Its velocity increases. What direction is its velocity, by the way? down. And you remember Galileo said that how much does it increase its speed every time?
By odd numbers.
By odd numbers. Which means that in the first instant it has fallen 1, second, 4, third, 9, fourth instant it has fallen 16. And these are the perfect squares. Remember that? And that tells us that the relationship between how far it falls and the force of gravity must depend on a square quantity. In fact, it's this. D equals 1/2 gt squared. You need to have this equation written down, where D is distance, measured in meters. You know what 1/2 is. Lowercase g is, we use this sometimes as specifically what acceleration? Due to, yep. Which, by the way, doesn't just have a unit. On Earth, we know this value. What is the value always? On Earth's surface. 9.81 meters per second squared. T is time measured in seconds. Shove all that together, and we can tell, what does this equation give us the power to do? Without having to worry about successive increments of distance, or having to worry about that it lands exactly, or not lands, but that it, at any given time, we're thinking about exactly one of these. We could put in a decimal value here. What does this give us the power to do? Just on a basic level, what does this equation tell us? Do we know this? Yeah, for Earth we know this. And it can be given for any other planetary or other large gravitational body. Do we know this? How could we find this out? What would be our measurement for this? Stopwatch. Yeah, we can time how fast it's going. And it'll tell us, tells distance. What if we knew how far it was going to fall, and we wanted to figure out how long it would take? Could we do that with this? Well, once again, do we have the g? Yep. We want to find t. Do we have the d? Yeah, I said we did. So, well, of course we could. Yeah, we definitely could. What would we have to do mathematically to it to do that? Manipulate. Let's manipulate it now. So I'm not going to change the values. Let's just manipulate to find t instead. What's the first thing I should do to find t instead? I could do that, but I'm not going to divide by t squared because I want to get t by itself. So it'd be easier for me, I think, if I get the other stuff that's with t over to the other side instead. So what should I do first? To manipulate, once again, we're manipulating this to try and find t. Say it again. Divide by 1/2 g. Okay, so that gives me what? D divided by 1/2 g equals, what's dividing by a half the same as? So 2d over g equals t squared, right? Now what? I would love to. I'm so glad you said that. Not everyone always gets that right away. So square root of 2d over g equals t. Write this one down too. Has all the same quantities as the one above it. It's just now solving for a different amount. Some people's books, I remember, I think my book has this exact thing, but some people's books had the square root of 2 times the quantity d over g. Is that the same thing as this? Yeah, it ends up being the same. It doesn't really matter whether the 2 is on the line or next to the line. So anyway, you can find the time. What if we wanted to find the velocity at any given second, at any given time t? Well, that's even easier. How are velocity and time related? Or, sorry, how are velocity and acceleration of gravity g related? Well, if we had this, how can I get velocity from this? Well, once again, we're using g instead of a because we're talking about gravitation specifically. But now, how can we get this? Yeah, it's just v equals gt. The reason the delta goes away, it still is delta v. It's just that we're assuming, since it's in free fall, it started from rest. It would still change in velocity. Let's be clear. It's still change in velocity. If for some reason you're throwing something down, then you have to add the starting velocity to it. It's still change in velocity, but this just makes it easier to express. So delta v, or just v, equals gt. There's another really easy one. Could we, and we're not even going to bother doing this one because it's so easy, but could we find If we were given a velocity and the fact that g on Earth's surface is 9.81, could we find time? Yeah, of course we could. It's just one step solving a manipulated problem. Make sure that I haven't missed anything. There's an excellent reaction time lab that I really wish someone would have done, maybe someday. And then your book also talks about, goes into detail about, well, a little bit of detail, about air resistance and how that affects it. But basically, the air resistance affects it in what way? Air resistance affects this in what way? Slows it down. The same amount for everything? No, remember, A is the same amount, or G on Earth's surface is the same amount for everything. I'm trying to think if I have a good example here just lying around. I don't love this example because it's damaging to property. But if I have these two things, which one weighs more? The book. And if I drop them, what should happen if physics is right? No, say it again. Try harder. What should happen if physics is true? These should both land how? At the same time. They did in my poor book. Why, if this were a feather, which it isn't, but if this were a feather, why would it not land? Or a Kleenex. That's a great idea. Why do these two things not land at the same time? Is it because this one's lighter? No. Has more air resistance. And the way we can tell that it's not because it's lighter is have something the exact same mass. We're going to assume these two Kleenexes in their manufacture process are the same, right? Which one's lighter? They're the same weight. Which one has greater air resistance? This one. So now they don't land at the same time. So we know, we just very, very easily, in an extremely simple experiment, proved, no, we can't say proved, but we provided a great deal of evidence for the fact that weight does not make something fall faster. And let me tell you, not just because it's Crawford, but if you ask anyone on the street I was going to say America, in the world, if you ask another human being, do heavier objects fall, I'm doing microphone thing. Do heavier objects fall faster than lighter objects? They will say, yeah, of course, I know about the world. Everyone thinks, no, not everyone, not physics students. It's very easy for people to think that heavier objects fall faster than lighter ones, but it's flatly wrong. And you can show that demonstration to them. You have two objects of the same weight, one's clearly falling faster, and the two objects have completely different weights, and they fall at the same speed. You know, I mean, it's not hard to disprove that incorrect hypothesis. So your book talks a little bit about air resistance. And then your book also talks about the charting, like the graphing of these, distance and acceleration. And it goes into a little bit of detail about the fact that acceleration is a derivative, I mean that mathematically, not just in the English sense, but acceleration is a derivative mathematically of velocity, which is a derivative mathematically of displacement. And the graphs show that too. So you should do a little bit of reading on those. We're going to do some problems with these. There are problems on your chapter review. And someone should do the activity that is the reaction time one. I really like that one. Questions? Questions. Does this help you at all? This should all be a review for one thing. What is really important that you get out of it mathematically, at least, which a large portion of your grade is these. I would say what the equations mean would be the main thing. In fact, that was your objective, was to describe, model, and calculate linear motion. This is the calculate bit. Bye. You have the rest of this class and I think tomorrow. Nope. You have the rest of this class and not tomorrow to work on your chapter review. How much time is left? Good. Get it done. I would have rather you had half an hour. But you have